Welcome back, and in this series of videos we're going to be looking at redox. You've already studied redox in the lower 6th year in Redox 1. In this pack we're going to be looking at redox titrations, and in the last pack on redox we're going to be looking at redox equilibria. So before we start Redox 2, it would be really helpful if you dig out Redox 1 from the lower 6th and go over that, as the first parts of this pack are just revision of your lower 6th work. So we're going to need your pack, the redox pack from the first year, and we're starting on page 1. So this is the first page of your notes, and we're just filling in those gaps on the first page. So we should know from our lower 6th work that redox is concerned with the movement of electrons, the loss and the gain of those electrons. We should also remember that an oxidation reaction cannot happen on its own, neither can a reduction reaction, because you need both a source and a sink for those electrons. So these two reactions always happen in pairs, and that's why they're called half reactions. So we put the two half equations or half reactions together to make a total redox equation. From lower 6th, you should remember how to calculate oxidation numbers, how to write out balanced half equations, and how to put them together to make a whole equation. And that's what we're going to look at on the next few pages. So if we take this as an example, NaHSO3, we do need to remember your rules from lower 6th, starting with the sodium. Sodium will always be +1 because it is a group 1 metal. So when it forms an ion, it always forms a 1+ ion. Hydrogen also always forms a 1+ ion unless it's with unless it's a metal hydride, in which case it's -1. And it's not in this case, so it is also +1. Oxygen is always -2 unless it's a peroxide or if it's with fluorine. So it's -2. Sulfur, well, we don't have a rule for sulfur, but we do know the oxidation numbers of the other three. So therefore, we can actually work it out because I have +1, +1, and then I have 3 -2, so that would be -6 in total. So that makes the sulfur +4 oxidation state. So the sulfur is the only one that has a variable oxidation state in this case. And there are lots more of those you can practice on page 3. So do make sure you've had a good practice at doing those. As I said before, if you get stuck, look back at your notes on how to work out the oxidation numbers from the lower 6th. But we're going to move on and look at half equations. So if I have iodide changing into iodine, this is a typical reaction. First thing I need to do is I need to balance it. Well, I have 2 iodines on this side, I need 2 on this side, so I put a 2 in front of the I-. So this is an oxidation reaction because it's going from -1 to 0. Remember, the oxidation number of any element in its standard state is going to be 0. So here the oxidation number is going up. That's why it's being oxidized. Oxidation is loss, so the electrons are coming loose. Now, each iodide is changing by 1 because it's going from -1 to 0, but there are 2 of them, so that makes 2 electrons. I can then just double check with charge balancing because I have a 2- side charge on this side, so I need a 2- on this side. So this is an oxidation reaction. I'm now going to look at a slightly harder one. If we look at manganate, MnO4-, and that's reacting to form Mn2+. And this is one that we're going to come across a lot. Now, first of all, we have to notice that we have oxygens present. Now, the temptation is to just put some oxygen on this side as O2, but we can't do that because that would be changing both the oxidation number of the manganese and the oxygen. So we've got to make sure we're careful with that. So to get rid of these oxygens, we're going to add acid, hydrogen ions. And those hydrogen ions can react with the oxygens to make water. in this case 4 H2Os, because I've got 4 oxygens this side, and that conserves the oxygen's oxidation number as -2, and I have 8 hydrogen ions to get it to balance. Now again, we can do this by charge balancing. We can also do this by working out the oxidation numbers. So the oxidation number of the manganese in this species, well, oxygen is -2, and there are 4 of them, which makes -8. The whole thing adds up to -1, so the manganese is +7. So it's going from +7 to +2, so that's the change in 5. This is a reduction reaction, because the oxidation number is being reduced, it's going down. The manganese is gaining electrons. So it's gaining 5 electrons. So that's my oxidation reaction and my reduction reaction. And I'm going to combine these two to make an overall redox equation. Now the thing to remember in an overall redox equation is that the electrons must cancel, because this is my source of electrons, this is my sink of electrons, and they've got to match. So I'm going to times this top one by 5 and the bottom one by 2 to get the electrons to cancel. I'd have 10 electrons in both cases. So my total redox equation would be 2MnO4- plus 10I- plus 16 H positives. We don't include the electrons in a total redox because they always should cancel, which goes to 5I2 plus 2Mn2 plus 8H2O. Okay, so the top one times by 5 and the bottom one by 2. We can go back and charge balance it, and you should see there it all works out as 4+ in total. So we'll look at another example where we're oxidizing iron 2 to form iron 3. It's a typical oxidation reaction, and it's quite easy because we're dealing with transition metals which have variable oxidation states, and they're quite easy to interconvert. Now to do this oxidation reaction, I need an oxidizing agent. In this case, I'm going to choose dichromate, Cr2O7 2-. This is another one that you should be familiar with. So the dichromate is going to be reduced to the chromium, Cr3+, and there are 2 of them obviously to balance. Again, I need to deal with these oxygens. I've got 7 oxygens on this side, so I need 7 oxygens on this side in the form of 7 waters. So I'm going to add 14 H positive. Again, I can work out the oxidation numbers where I've got 7 oxides, that's 14, -2 in total, that's 12, and then divide by 2 to get the chromium as +6, and it's going to +3. So each chromium is changing by 3, but there are 2 of them, so that makes +6 electrons. Again, I can do the charge balancing to check I've got it correct, because I've got a positive 6 on this side, 2 lots of the 3+ ion, and I've got the same on this side, so that charge balances. Now to put these together, all I'm going to do is times this top reaction by 6, because I need 6 electrons here. And you get 6 Fe2+, plus your dichromate Cr2O7 2- plus 14 H positives, going to 2 Cr3+, plus 7 H2O, plus 6 Fe3+. And again, you can check by charge balancing that that all works.